I'm just going to put the lights down. There we are. Oh, is that a bit dark? No, I think that's fine. Or do people feel they need to take notes? Let's see. No? All right, let's have the lights down. Yeah. Normally this is sort of halfway house. Well, I'm delighted to be back and see so many of you, including some familiar faces. So that's always a pleasure to return to Cape Town, where I spent so much of my career. Well, this is the topic tonight, and this is one of my favorite talks because mostly when I talk about astronomy, I'm basically telling you how it is, and you just have to accept that. But in this particular talk, I'm going to present you with evidence, and essentially you will have to draw your own conclusions because we simply do not know the answer. So I'm going to start off with some provisos, and then I'm going to make a case for life being widespread, and the idea that therefore, one might consider life to be, intelligent life to be quite widespread throughout the galaxy, if not the universe. And then I'm going to sort of review the development of what we know about the development of life on Earth, and, and then talk about some of the ways that we are looking for life elsewhere, and then maybe just draw a few general conclusions, as you will see. Well, what is life? Well, I thought this is a definition produced by NASA, and I think it is an extremely good definition: a self-sustaining chemical system capable of Darwinian evolution. So that is very different from the kind of chemistry one did at school, where you mix things together and you always get the same chemical processes occurring and the same outcomes. This is clearly a much more complex chemistry, where slight deviations in the controlling system will slightly but not completely change the outcome. And I guess we could spend the whole evening debating this, but I think we'll just accept it as read. So what do we mean by life? Well, clearly there is a hierarchy of life. And the most simple life that we know of are the single-celled organisms. And then, clearly, there are single-celled organisms, things like bacteria, archaea, those sort of things. And then we come to multi-celled organisms, simple multi-celled organisms, things like algae, jellyfish, things like that. And then in our hierarchy, we come to the more complex organisms, and the issue of consciousness and the question of self-awareness creeps into the story. And clearly a dolphin is conscious. To what extent it's self-aware, to what extent it is able to communicate, to my mind, still open questions. But then we come to a communicating, self-aware, self-conscious civilization, and I epitomize that by this Greek vase here. Now, clearly, if the universe, or if the galaxy, and I guess we should confine ourselves to the galaxy, was full of civilizations at this level of development, we would know nothing about them, because we would have no means of communicating with them or of receiving evidence of their existence, or maybe only very, very subtle means. And so when we come to the business of communication, and that is really the only way we are, at least in the foreseeable future, going to know about civilizations elsewhere in our galaxy, then we are talking about technologically advanced civilizations. And of course, we've only been in that state for a short time. So there are, again, many provisos that there could be a lot of this around and we would know nothing about it. And so the universe would appear quiet. Now, the other thing is we have to decide that can we be certain to recognize life? And I don't really mean because it would look totally weird like these odd lobster things, product of somebody else's imagination. Life is most likely to be based on carbon and water because of carbon's unique chemical properties, but it might operate at much lower temperatures, might operate around silicon, and might use quite different solvents, maybe the methane and ethane that we see on the moon in our own solar system. Now, or perhaps a greater problem might be that it operates on quite a different time scale than we do. If you think about ourselves, our hearts beat about once a second, and we are allowed about 2,000 million heartbeats in a mammal's lifetime. Some mammals' heart beat very fast, some more slowly. But that's about a lifetime. If you think of our everyday lives, perhaps the finest sort of element of memory or self-awareness, you might say, was a tenth of a second, a tenth of a heartbeat or so. And that's, you know, just a very, not easily, just the sort of number that one pulls out of the air. But now imagine there might be some kind of organisms around whose heartbeats only beat once a year. Now, if they were at an advanced level of civilization, the signals that they might be sending into space for us to detect would be changing at such a low frequency that we might never notice them as, coherent artificial signals coming from elsewhere. So again, there are a lot of provisos. There are a lot of scenarios we could imagine that might allow the existence of an advanced civilization, a technologically communicating civilization that we might still not recognize. Now, what do we know about life? Well, one of the things that we've certainly discovered in the last 10 or 15 years, that life on Earth is widespread and tenacious. And these images here correspond to different environments where living organisms naturally exist. Lake Mono, with its very high levels of arsenic. NASA produced a press release that turned out to be complete nonsense, suggesting that the DNA in the organisms living here had substituted arsenic for phosphorus. Chemically not possible. In fact, the organisms are loaded with arsenic, presumably because they're trying to, chemically, arsenic and phosphorus are similar. They're trying and get the tiny bit of phosphorus they need. But nevertheless, that would be highly poisonous to most organisms. If we come to these hot springs, they are colored by organisms living in water close to boiling point. If we go to the Antarctic, we can drill ice cores that are 100,000 years old at temperatures of -40, where we find this Colwellia still viable. In fact, it may even be viable at liquid nitrogen temperatures. And if we go to the smokers in the mid-oceanic ridges, where the temperatures run from 90 to 120 or so or hotter, superheated water coming out of these things, rich in chemical elements from the black smoke there, we find this particular organism that only really thrives at the temperatures at which we're normally sterilizing materials. So if you think about it, it would be impossible for human beings to eradicate life completely from Earth. And even if they eradicated all this from the surface, we find living organisms nearly 3 kilometers deep in basalt rocks that don't appear to rely on photosynthesis. So life is widespread and tenacious. But of course, it's simple single-celled organisms. And perhaps the record for the oldest viable life comes from this 250 million year old salt deposit, where in the liquid brine inclusions you can still find evidence for viable bacteria, viable single-celled organisms. So life is widespread and tenacious. We live in a universe perfectly suited to our existence. What do I mean by that? I mean that the laws and constants of nature seem to be very finely tuned to produce a universe that has produced the stuff of this room and allows us to live in it. And one of those examples of fine-tuning is the relative strength of the force of gravity and the electrostatic electromagnetic force. And there's a factor of 10 to the 36 there. If gravity was any weaker, then the universe, then stars would have not formed. If it was any stronger, then everything would have probably ended up disappearing into a black hole. Now, why is that? Well, because there may be some as yet undiscovered super theory that links all the constants of nature together. However, the most favored idea at the moment is the idea of the multiverse, the idea that in reality our universe is not just the one we observe, but there are maybe 10 to the power 600 possible different universes, all with different constants of nature, and so naturally life only appears in those that happen to be finely tuned. And of course, if you are of a religious bent, then you may believe that our universe was created by a God, and in which case you have the intellectual problem of deciding in which universe that being exists. So, within our universe, there are many galaxies, and here is a typical galaxy like the one we live in. There are 100,000 million stars in a typical galaxy like this one, like, as I said, the one we live in. So 100,000 million possible places to have a planetary system just in that galaxy alone. And when we look deep into space with the Hubble Space Telescope to distances that correspond to a time when the universe was about a 20th its present age, we look at a small area of sky, we see essentially all the galaxies in the observable universe. We go back to a point where galaxies were still merging to form the sort of galaxy we see today, and we can just, this is an area, 100th the area of the full moon, so you just scale that up to include the whole sky, and the number you get is, again, about 100,000 million. So 100,000 million stars in a galaxy, galaxies in the observable universe. So an awful lot of places where there could be life. And just to put us in the picture, because astronomers are often accused of dealing just in large numbers and awing people with their vast numbers, there are about, well, I'm told about 80,000 million neurons in the human brain. And of course the difference is that in the human brain, they're all multiply interconnected. So a lot of places where we could have planets. When we look inside a galaxy in a bit more detail, we see these dark regions here where stars are being formed. They're called giant molecular clouds, and the giant molecular cloud overfills the screen here. This is just the center of it, eaten out by the newly born stars, and it is called a giant molecular cloud because it is sheltered. The gas deep inside here, which you can't see because it's too cool, is full of molecules. Molecules that are not destroyed by ultraviolet radiation from the stars because they're protected. And this table summarizes the molecules that were known. This is I think there are 129 molecules here. The present score is about 169. And you're not meant to be able to read the table, you're just meant to marvel at the number of entries. And indeed the complexity, 8, 9, 10, 11, 12, 13 atom molecules. And amongst these are some of the basic building blocks of sugars, potentially of life. So they're the building blocks out there. Now, the other thing we've been doing in recent times, again in the last 10 to 15 years, is actually discovering planets orbiting other stars. And this table was quite an early table, so it's long out of date, summarizing the planets here and the distance, summarizing the stars with their planets. So that's the star, it's got a planet here, and some of them got more than one planet. and they are compared here with our own solar system and the position of Earth, Mars, and Jupiter. And if you look at this table, you will see that the planets are mostly the size or bigger than Jupiter, which is 300 times the mass of the Earth, and they're mostly close to their star. So these are solar systems rather unlike our own, but we put that down to an observational selection effect. Because what we were detecting was not the planet itself, but the effect of the planet on the star as the planet and the star both orbit the common center of gravity of the system. And whereas this thing may be moving at 30 or 40 kilometers per second, this thing is only moving at a few meters per second. So we're detecting evidence for the planet. So it's clearly that one is going to select in favor of large planets or massive planets orbiting around lower mass stars because they're easier to detect. And so that when we plot a graph of planet mass, and these are in terms of the Earth mass, 10, 100, 1,000, this is logarithmic, against the distance of the planet from its star, we find lots of, these are the ones we've discovered, there's a kind of observational selection effect here that means that these planets down here are moving too slowly. And you will see when we compare that with our own solar system, Mercury, Venus, Earth, Mars, Jupiter is massive enough that we're finding lots of Jupiters, and indeed some of them at typical Jupiter distances, but when it comes to Earth-like planets, there is still an observational selection limit there. Now, since then, we've had another experiment, which sadly only lasted for about 3 years or so, the Kepler mission, staring at an area of sky and looking for the eclipse, the dimming of light of a star as a planet moved in front of it. A typical, maybe Venus transit would be about 1 part in 10,000 or so. And this has brought in a whole new haul of planets, but so the diagram is filled up with the pink, and you can still see, although we're now detecting Earth mass planets, probably, and not all of these have been confirmed, they are not typically at Earth distances from their stars. So if you're too close to your star, then it is too hot. And sadly, there's another observational selection effect. It takes the Earth a year to go around the sun, and this thing broke down after 4 years. So you've got to have a number of transits before you can confirm that that's what you're really seeing, and it's not variability in the star. Okay, I should have cut that out. So what counts is that the planet must be in what's called the habitable zone. That is the region where water is liquid, and so if you have a faint star, then you can be physically closer, or a brighter star than the sun, you must be physically further away. And the size of these symbols summarizes the predicted masses, and you can see by just glancing at this diagram, although there are some fairly Earth-like objects that have been discovered, despite the fact that the planets we've discovered run into 1,700 or so now, there are only perhaps 1 or 2, and even those are not really very satisfactory comparisons with the Earth. But nevertheless, we are still working on this, and we think that we still have a big observational selection here. It's still difficult to detect Earths going around other stars. So I think we can still say the case for life being widespread, and possibly then, therefore, intelligent communicating life, is really quite strong. The universe is perfectly designed. It's full of the building blocks. There are many stars, there are many planets, perhaps more planets than stars, and life on Earth is tenacious. So you might think we've come nowhere in the last 2,400 years, because 400 BC, Metrodorus said it goes against nature in a large field to grow only 1 shaft of wheat and by analogy, in the infinite universe, only one living world. But just because something seems reasonable does not mean it's true. Now, the problem we have in looking for intelligent life elsewhere, which we're just going to focus on for a little while now, is that we have the problem of statistics of one. We only have one example of a planet that has an advanced technology epitomized by this nighttime view of the Earth. Look how the Nile is defined and the Trans-Siberian Railway, these strings of villages. Okay, so what I want to do now is to do something that in a way is sort of going against one of the principles of modern astronomy. And it really goes back to 1543 when Copernicus relegated the Earth from the center of the universe. He realized you've got a much simpler model of things if you put the sun at the center of the solar system and had the Earth going round it. And okay, had the stars. So the sun was at the center of the universe. But the history of astronomy and astronomical discovery since then has been one of continued relegation, as we realized that the sun was a very ordinary star, not particularly bright as stars go, that it was on the outside of a very ordinary galaxy towards the edge of one, and that our galaxy is in a very small cluster of galaxies. And it's almost become a principle now that if we find in cosmology or elsewhere that we seem to be living either in a special place or at a special time, then that kind of observation is treated with a little bit of suspicion. Doesn't mean it's wrong, but it's treated with suspicion. So what I want to do now is slightly go against that principle and just put to you the way I see things have been put together and suggest that maybe they are a little bit more special than we might think. Although I suppose I should try and be neutral about this. Okay, our sun is a stable star halfway through its life. You've got to have time, it would appear, looking at the Earth, for complex life to evolve. Now, about 16% of all stars are F or G stars, as we say, a bit like the sun, in other words. Although, interestingly, the Kepler mission showed that amongst stars like the sun, our sun is a lot more stable than the average star. So maybe there's something there. Okay, 16%, lots of stars like that. Now, the Earth. Well, it's quite plausible that in every solar system there'll be a planet in the habitable zone, i.e. where water can be maintained as a liquid. Now that, you might say, there's always one. But the mass of the Earth is also critical. If the mass is too small, the convection in the interior will have stopped, the magnetic field will have disappeared, the atmosphere will probably have been stripped off. And then the water goes with that. If it's too massive, then maybe it retains either too much water or an atmosphere that's too rich in hydrogen and helium. So the mass is important, and we don't have any statistics on the mass distribution. Now, another rather unusual thing about our Earth is that it has a very large moon in relation to its mass. The moon has a mass about the same as the mass of the moons of Jupiter, and Jupiter is 300 times more massive than the Earth. Now, we believe that our moon was created in quite a different way to the moons of Jupiter. Our moon, we believe, was created very early in the history of the solar system when a Mars-sized planet collided with the Earth, stripped off some of its mantle, was destroyed, created a huge ring of debris out of which the moon coalesced. So you have to say, does that kind of event take place in most solar systems? So why is having a massive moon so important? Well, it has a stabilizing effect on the inclination of the Earth's axis of rotation. And as you all know, because in those days they used to teach about how the seasons were, this is the cause, this inclination of our rotation axis compared with the plane is the thing that gives us the seasons of summer and winter. Now, our inclination axis varies on a time scale of about 40,000 years by about plus or minus 1.5 degrees. And certainly in the last few million years, this slight variation has been enough to trigger the onset of ice ages. So clearly it does have an effect on climate, even that small effect. Mars, on the other hand, has no stabilizing moon, and its inclination on a rather shorter time scale varies by plus or minus 15 degrees. Now, if we had that sort of effect going on Earth, we would have very extreme weather systems, very extreme contrasts between seasons that might not have made the Earth unsuitable for simple life, but probably would have been a great barrier to the development of a more advanced civilization. Okay, what else is special about the solar system? This takes us back to 1994, when we saw an object, a comet, colliding with Jupiter. And this is the debris plume catching the sunrise around the edge of Jupiter. Now, we believe that the way evolution works on Earth is through what is called a punctuated equilibrium. So it's not a continuous process of change, or, well, there may be a continuous process that is driven by slowly changing maybe climatic or other conditions, but the major changes have occurred as a result of a catastrophe, when the number of species and the number of members is considerably reduced to small isolated communities, and that evolution progresses quite rapidly as those isolated communities repopulate all the available ecological niches. So what we need are comet impacts, occasionally, but not too many. And Jupiter, in its location, certainly governs the comets coming into the inner solar system. Now, in a more general way, there are some grander constraints, and one of those is the whole evolution of the universe itself. Because when last time I came, I talked about stellar evolution, and I told you that everything in this room had been made inside stars since the beginning of the universe. So the universe has to be going for quite a while until we have built up enough heavy elements to actually make planets. And basically what this diagram shows you is this is a distribution of stars that have planets, and it's a distribution of the abundances, the amount of iron in those stars. So the stars that have the same amount of iron as the Sun and the Earth correspond to this black line here. Well, sorry, there's the Sun, because we don't know about their planets. And we go down to about 1/10 as much iron as the Sun, and then we find no more planets. And we do observe stars with 1,000th as much iron as the Sun. So clearly the universe has to have been running for a while. So perhaps we've only had the opportunity for life in the last third of the life of the universe. Maybe a billion years longer than that or so, to account for these stars here. And lastly, the special thing about where we live is our location towards the edge, the safe zone, if you like, of our galaxy. We are out here 25,000 light years from the center. We orbit at about 200 kilometers a second, going round every 200 million years or so. And there aren't too many giant molecular clouds this far out. There aren't too many supernovae that might bathe us in damaging ultraviolet irradiation. And so we call that the safe zone. And what do giant molecular clouds do? They perhaps upset the comets that surround our solar system about a couple of light years away. The pool of comets in the Oort cloud will feel the gravitational effects of not only nearby stars but giant molecular clouds, and they might come pouring into the inner solar system, causing havoc. So I would suggest that perhaps our solar system is a little bit more special than we think, and perhaps therefore has been a place where it's been possible for life to develop and for an advanced civilization to emerge. Now, what I want to do to sort of, well, support or add to that is just to look at the development of life on Earth. And with the arrogance of an astronomer treading into somebody else's territory, I summarize the history of life on Earth in one slide, from the formation of the solar system here, the creation of the moon here, to today, and here we have the mammals, perhaps even a bit too thick, that little red bit there. So let's just look quickly at the history of Earth. We have an event here called the Late Heavy Bombardment, and this was an event we used to think that at this moment in time, we know that Neptune and Uranus triggered the inflow of a lot of material from at the edge of the solar system that bombarded the planets, and when we look at the moon today and see all those craters on the moon, most of them came from the late heavy bombardment about 4,000 million years ago. And we used to think the Earth might have been completely re-liquefied at that point. We're not quite so sure now, but let us just move on to the oldest known rocks are about 3,800 million years old. And then almost as soon as it could, we see evidence for the oldest traces of life in certain sedimentary deposits where we see evidence for life. So life seems to have appeared, and this is mystery number one, almost as soon as it possibly could. And that is mystery number one. We don't know where was that life spontaneously created, did it come from elsewhere? But then comes a period when for thousands of millions of years we had nothing but single-celled organisms, up to a mere 600 million years ago when there was a sudden burst of multi-celled organisms, in fact the progenitors of all the organisms that we see on Earth today. So what caused this second transition? That is perhaps another mystery. So when you just bear in mind, when you're looking for Earth-like planets, if you came to the Earth at some random moment in its history, chances are you'd have come at a time like this and seen nothing but bacteria if you were lucky, or the equivalents. Now, something important was taking place. We started off with bacteria-like things called prokaryotes, and these multi-celled organisms are all... Whoops. Oh dear. I don't know what happened there. Now I know what's happening there. There's no power on this plug here. Have we got our IT man at the back there? Can you make this plug come alive? It tells me I'm on reserve battery. How do we get that to? Is it? It's obviously not. No. No. It came on briefly. Then let's see. It's probably just a faulty. Just jiggle it. There we are. Okay, it is charging now. It is charging. Let's just, okay. Take your finger off. Is it going to stop charging? Right, hang on. We've got another solution. I'm not, whoopsie. Sorry. I'm just going to mute myself for a moment. I've got a double adapter that so we can go into the next plug. Find out where in my bag of tricks this is. Let's just try that. There we go. Okay, let's just see if we're close to. Okay, good. We're back in business. Thank you. Okay, right. So I was talking about the simple prokaryotes, bacteria-like, then all the modern multicelled organisms are made of eukaryotes, which appear to be some kind of symbiotic combination. It looks as though bacteria have been incorporated inside this more complex cell. Things like chloroplasts and mitochondria have their own independent DNA, and they reproduce within the cell. So at some point here, this strange symbiotic cell was created that is now the progenitor of all these organisms here. What else was going on during this time? Well, there was a steady build-up of oxygen. And so the oxygen levels were increasing in the water and then in the atmosphere, and it is possible that the great proliferation that took place 600 million years ago was triggered by the fact that the partial pressure of oxygen was now high enough that if you had a spontaneous clustering of cells, the cells in the middle would not be starved to death. Enough oxygen would diffuse through. But anyway, when we look at the broad history of life on Earth, we see there was a huge interval of time with nothing but single-celled organisms, and this mere 600 million years ago, this sudden proliferation. Now, when we look at the last 600 million years, here's 600 million years, and we come to the mammals here, and the first hominids, which are probably, even that's a bit too large, the last 7-10 million years there. So what do we see? Well, we see the emergence of animals and plants coming on land, but we see these 5 great major extinctions, these great catastrophes, mass extinctions, when the number of species were reduced by very large factors. We know something about this last major extinction, 65 million years ago. We believe, although it's still argued, that this may have been triggered by a very large impact of a comet impact, comet-like object, but it also coincides with a major volcanic, the Deccan Traps, a major pouring out of eruptions in what is now India. So we know that we owe our origins to this last catastrophe, the end of the age of the dinosaurs, the emergence of the age of the mammals. These other catastrophes, we don't know exactly what they are. It probably was a combination of climate change, volcanoes, impacts, and perhaps the distribution of continents that were drifting and colliding and breaking up was an important factor. But now, what you have to ask yourself, is this an inevitable trajectory, or is there a huge element of chance that you start from here and you end up here? So that is just another of those open questions. And perhaps one last point I would like to make is that you'll see a thin red line here. The rate at which species are disappearing today would, in some future geological deposit, look like a potential major mass extinction, and we know what is responsible for that. Okay, let us look at the last 7 million years now of the evolution of the mammals, and we go back 7 million years till we see the last common ancestor between ourselves and chimpanzees. We had a common ancestor then, and for the last 7 million years we have been evolving and somehow merged up here, and chimps have also been evolving. And this diagram summarizes some of the many names that may be familiar to you of hominids or hominins that are found mostly in Africa, and the people who drew this diagram made a careful point of not drawing a trajectory through here to show how we are directly linked, and if we are directly linked. But within the last million years or so, well, we see Homo sapiens, that's us. we see Homo neanderthal here, and of course it's only within the last few years that we've recognized that we contain maybe 2 to 3% of the DNA, at least people from Europe, people from Asia contain the DNA of Denisovans, so there was some interbreeding between those. So that is us up there, and we don't quite know how we're related to the rest. But it is also felt that there was some major event that took place the order of 1 million years ago when fire was used to process meat. And in that processing and general cooking, it was the proteins, the materials of food were made much more easily accessible to our digestive systems. It required much less energy to digest foods that were gathered and caught, and that was perhaps the stimulus, that extra energy that allowed the development of the human brain, and the human brain does consume a significant amount of energy. And after this point, some people recognize what they consider to be the fundamental thing about us as human beings, and that is this emergence of mind that perhaps took place, well, maybe 1 million, maybe 800,000 years ago. Now, there's some discussion about that. Darwin considered, of course, the emergence of mind, and he thought the difference between humans and animals was one of degree, not a fundamental difference, just a sort of, elaboration, extension of some of the faculties that animals had. This person, on the other hand, who epitomizes a different point of view and wrote this nice, easy article in Scientific American 2009, while he marvels at the abilities of animals, believes there's a profound difference between animals and humans. Now, we used to say that tool manufacture and tool use was a human ability. It was a uniquely human ability, not just a human, it clearly is a human ability, that it was a sort of definition of, the emergence of modern humans. But we now recognize that here Betty the Crow, who was operating in a laboratory in Oxford, had a problem to solve, to extract a bucket with some meat in it that she wanted to eat. And she didn't just select a hook, she actually bent a hook out of a piece of wire and then used that hook to hook the bucket out with the meat in it out of the experiment there. So clearly this is a clear sign of intelligence and tool use. And corvids are quite, the difference between them and the evolutionary tree and ourselves is really quite large. So intelligence is not necessarily the marker we're looking for. It's something much more profound. And this looks a bit crowded. And I would just go through it very quickly. It's a summary of what Mark Hauser says. He notices that animals and humans use tools, solve problems, exhibit social behavior, and even object to unfair food distribution. But he isolates what he thinks are uniquely human abilities that emerged perhaps within that last 800,000 years or so. What he calls generative computation, the limitless variety, combination of words, notes, mathematical symbols, a combination of ideas, social relationships, moral values, the use of mental symbols to encode sensory, real and imagined experience, and to exhibit abstract thought about, unicorns, God, the universe, unicorns, all kinds of things. And he uses this particular sentence. This is just something to illustrate what he means by those things. This sentence, we decide it's forbidden to intentionally push someone in front of a train to save the lives of 5 others, is a statement, a contentious statement that we could debate, and he just shows how this consists of these different domains of thought. The motor domain, pushing somebody in front of a train, the train as an object. we have the concept of number, and the moral domain saving lives. So that is what he means by the emergence of mind. Now, will that always happen? Okay, let's now look briefly at the last 200,000 years, which is typically maybe the time for the emergence of Homo sapiens, 150,000, 200,000 years. And within the last couple of weeks or so, we've seen the publication of perhaps the earliest example of organized human behavior. This structure, this wall that's dated to that made of stalagmites that have been broken off and with signs of burning along the perimeter of the wall. This is deep inside a cave. This thing, there you are, it's about 5 meters across. This has been dated at 175,000 years old. So it turns out it's probably the oldest example of this organized human activity. If we look at the last 100,000 years, and then we come, of course, to the southern Africa, where we've seen these excavations at Blombos, showing examples of the carved ochre, perhaps the grinding of ochre 100,000 years ago. These are the earliest recorded examples of what you might call human artistic activity. And you have to now ask yourself, is it inevitable that when you get to this stage, and perhaps this stage, that eventually you will go through all these stages and we will visit the moon? Is this an inevitable trajectory that once 100,000 years ago, when people were grinding ochre, that we would be building rockets and flying across the world and visiting the moon and sending radio signals and building lasers? Is this an inevitable trajectory, or are there many other stumbling blocks and possibilities and possible outcomes that could have occurred here? And it's worth emphasizing that really this interval here is really the duration of the last ice age. So it was warm back there, and then the last ice age came to an end about back here sometime. So in geological terms, a very rapid, a very almost exponential climax to the whole thing. So what I'm suggesting is perhaps that it is a bit unusual that we are where we are, that it's not inevitable that given a nice habitable planet, you will have an advanced technology. Okay, now if it comes to single-celled organisms, then I am much more positive and optimistic. And basically, even within our solar system, I think there are many places where we might expect and hope to find single-celled organisms. Now, I want to go these very quickly. You can see evidence for water on Mars, and you see evidence for seasonal variations on the surface of Mars. Are we going to see seasonal variations? No, we're not. Anyway, we might have done. We don't have, that's another talk. Yeah. We see evidence for, when we look at the moons of Jupiter, we look at Europa and at Ganymede. Let's look at Europa. Doesn't look very exciting there, but when we look at Europa in detail, we see these great icebergs that seem to be frozen into a sea of ice. And where there is frozen ice, where there are broken icebergs, then below that we expect to find liquid water. And interestingly, the heat for this particular moon comes not from the sun, but from the gravitational torque, the gravitational flexure of nearby Jupiter. So there is the source of energy that may be allowing life to live beneath the surface water, the surface ice, comes from not the sun, but from just the gravitational force of a planet. When we go and we look out to Saturn, we see this moon Enceladus, and when we look closely at Enceladus, we see jets of steam, jets of water vapor or whatever, water gas, H2O, coming out of the bottom, again, tidally generated. When we look at one of Saturn's other moons, the moon Titan, we see these strange enigmatic features through its thick atmosphere, rich in nitrogen. We see features like this clearly estuarine. We see the winding rivers, this estuarine structure, but water is as solid as rock here. It's about minus 190 degrees or so, and these lakes, these pools of water, these rivers of liquid, are not water but something like ethane and methane, a whole other possibility for the possibility of forms of life. And so we have a number of places in our solar system where we might hope to find simple life, and we have a means of moving life around the solar system. This is a meteorite struck off the surface of Mars that has spent a few millions of years in the solar system before colliding with the Earth. And experiments have shown that bacteria can not only withstand the vacuum of space, but the accelerations that some of these rocks might have experienced. Now, clearly, the exciting thing about looking for life elsewhere in the solar system, even though I'm confident it'll only be single-celled, is to see whether it's structurally, in terms of RNA and DNA, identical to life on Earth, in which case we'll say, oh, well, it was just moved around from one planet to the other. Or is it in some way fundamentally different so that we could say life forms spontaneously wherever it's possible? If we are going to study the possibility of life on other planets, then we will need something like this project that was sadly abandoned to launch to launch a series of mirrors into space that would work collectively to make an optical telescope that was perhaps tens, if not hundreds of kilometers in diameter. You just make sure they work coherently, and then it would be, this is a simulation of what this telescope would be able to see from about 30 light years away, looking back at our solar system. It could use techniques to cancel out the light of the sun, and we'd see our planets, and we could form a spectrum and then analyze the spectrum for gases. Another project that has not been cancelled, which seems far more fantastical in some ways, is to launch a big disk into space, and this is called the New Worlds mission, that would sit a mere 130,000 kilometers in front of the James Webb Telescope and would effectively just mask out the light of the star and let you observe the planets around it. And it has this funny petaled shape so that the central diffraction image of the star, which would otherwise appear, is cancelled out by the funny shape there. So it would be able to reduce the brightness of the star by a factor of 10 billion or so. So then we could get a spectrum, and we could look for things like oxygen and CO2. Now, what about intelligent life? Well, you've probably heard of the SETI project, been going for many years, discovered nothing, still going, still discovered nothing. Now, we now know that the most effective way that we could communicate if we wanted to would be to use lasers. Lasers are, the most powerful way we have of sending a collimated signal a long way into space. And with today's telescopes and today's lasers, we could send a beam 1,000 light years, that's about that distance in the scale of the galaxy. We could send it 1,000 light years, and we could detect the signal with today's telescopes and today's technology. There you are, 10 to the 15 watts in 10 to the minus 9 seconds would give 1,000 photons at that distance. Quite capable. And so we have telescopes that are looking for such signals in case they're being sent. This one here is been going since 2006, and this one has been going since 2011, and both of them have discovered nothing. So the problem is, it seems to be silent out there. Now, this problem was addressed, now, silent in terms of advanced civilizations. I have to keep reminding you that technologically advanced. This was addressed by Frank Drake in 1961, who tried to calculate the number of communicating civilizations we might find in our galaxy. And it was written in terms of the rate at which stars are born, then some factors, and the lifetime of a communicating civilization. Now, I've just changed this round a bit. It's exactly the same equation, working out the number of communicating civilizations, only this time this is the total number of stars in the galaxy capable of having the right sort of star, and these are a load of factors that we'll come to, and then the lifetime of a civilization divided by the lifetime of the star. It's just expressing the same thing in the same way, and then we just collect, we put these terms together here. We've still got the big, that left that, the lifetime of the civilization at the end there. Okay, let's move on. Why have we done it that way? Because we know some of these numbers. Number of stars of the right sort in the galaxy, the average lifetime of those stars we know from stellar evolution calculations, and here is the first of these factors here, and the fraction of stars with planets, and we could set we can set that number. So the blue numbers we know, and so we're now going to try and calculate the number of communicating civilization. So the number of stars in the galaxy, 100,000 million, the fraction of stars with planets, the fraction of G to K stars, and the fraction of planets that we've so far discovered, with some quite generous limits on the size of those planets that live in the observable in the region where water would be liquid. And then we have the other factors that he put in: number of habitable planets per star, fraction on which life arises, fraction of those that evolve intelligent life, fraction which choose to of those which choose to communicate, and then the lifetime of such civilizations. Okay, sadly I have to go through this a bit quickly. So we can take the blue numbers here and put the numbers in, and they come out to be 0.2. And then we can just, you see it's getting simpler, number of habitable planets per star. We just set all these to 1. And that essentially means that every star that could has a planet that decides to communicate. So they're all set to 1. So then that is, how long does a civilization last? Well, 1 million years for a civilization. There'd be 200,000 civilizations in our galaxy. The place would be swarming with them. But 1 million years for a civilization. Let's go to 100 years. Now that may be very optimistic. This is pretty jolly pessimistic, because we've been around technologically communicating for 100 years. There would only be 20. So with all these options being set to 1, there's still only 20. So if we just put these down to 0.1, which is still 1 in 10, still 10%, still quite a big number. 10% would not be a risk you'd accept in any like flying in an aeroplane or anything. Then the numbers start to go down rather rapidly. And if we then find we'd have to have a civilization lasting at least 50,000 years for there to be one around at any one time in our galaxy. And perhaps this is what this silence out there is telling us, and that is that perhaps technologically advanced civilizations are not that stable, that they don't last that long. So what might be the threats to our existence if we are thinking that we've got to be around not just for a couple of 100 years or so, but for significantly longer? Well, I think probably the greatest threat that we face, and this is something Martin Rees addresses in Our Last Century, is ourselves. And he addresses that in a sort of optimistic way, that we do have major challenges of human-induced climate change, of shortage of resources, of political strife and so on, things that he feels that if we can overcome in the next 100 years, then, you know, we could have we could be running for a long time. But these are challenges we will face within this 100 years. If, on the other hand, we're going to, we're looking at a longer time scale, then climate change, whether or not it's induced by human beings, is something that has been occurring at least in the last few million years on timescales of 100 to a few thousand years. So we would have to accommodate, live with that. Every 100,000 years we get these supervolcanic eruptions, comet impacts, perhaps major ones on that kind of time scale. And then we have the whole issue of a typical species only lasts, about 1 million years before it dies out and it's superseded by some other, some different species of mammal. And then, of course, there are things like supernova explosions and so on. So let us now just look on a slightly longer time scale at the future of life on Earth. Now, we've already looked at this bit, the birth of the solar system here to the present day, the single-cell life, the multi-celled organisms here, and here we are today. Now, people have considered what might be the ultimate fate of the Earth, and the ultimate fate, of course, is the fact that the Earth falls into the sun. At least that's what the latest suggestions suggest. The latest calculations suggest, because the sun becomes a red giant and its atmosphere overwhelms the Earth and the Earth is gasified. We're not quite halfway through our life, although the oceans would start to evaporate long before we get to that stage. People who've thought a bit more about this, about the actual biology of what goes on, suggest that the crisis we may face in 500 million years is one of the depletion of carbon dioxide, believe it or not. The sun is already 30% brighter here than it was here, and it will continue to increase in luminosity. And what they are suggesting is that the added raised temperature will speed up the rate at which CO2 interacts with rock and is locked up. That's a thermostat that actually helps us overcome problems of CO2 at this stage. That will run riot. It will suck up all the CO2 in the atmosphere, and plant life will die out, rapidly followed by mammals, fairly rapidly followed by even the most primitive life. Now, it's possible there will be some evolution that compensates for this for a while. So it looks as though we may not have so much time to go. But let's be a little bit more optimistic. Let's clean the sheet again and consider the following. With today's technology, i.e. the ability to launch rockets into space, we could, in principle, imagine with today's technology how to build a spacecraft that lifted off the Earth, that carried life, and with today's technology traveling at the escape velocity of the Earth, 11 kilometers per second, in just over 1,000 million years, we could visit every star in the galaxy. Because that would be the crossing time. That was how long it would take. Now, 1,000 million years, that's twice as long as the interval that it has taken us to go from single-cell life to the present day. I mean, sounds crazy, but that is the timescale. And that, of course, is the Fermi paradox. Why is the galaxy not already being populated by civilizations moving out into space? Well, that's super optimistic. Let's be a bit less optimistic. Let's imagine that we completely screw up and destroy every blade of grass, every mammal, every tree that we see on the surface of the Earth. Well, that would take us back to there, and, well, we've got another, in 600 million years we went from there to there, so maybe, it'll be touch and go whether evolution would carry us through to that point before all the CO2 got mopped up again. So I'm sort of optimistic. There's really, whatever we do to the Earth, we're unlikely to eliminate all living forms, although we could very easily be eliminating ourselves. And perhaps if this lecture has any message, especially to the younger generation, and that is perhaps the silence out there is an important suggestion to us that we ought to be very careful about how we manage our world. Now, there are other possible futures that I haven't considered, and that is that organic intelligence is superseded by machine intelligence, something I've never taken very seriously until I think we understand the nature of consciousness, but far better people and wiser people than me do take this very seriously and think that this may even occur within a timescale of 100 years or so. And if that was to happen, and if the universe was to be filled, or the galaxy, with that sort of thing, then the Earth might go completely silent as far as outside observers would think. Okay, I'm just going to round up now with some final thoughts. Are we the most complex beings in the universe? I don't know. If there are other civilizations, will ours last long enough to make contact? And what would be the consequences? And if we are the only thinking, self-aware beings in the universe, is it important that we survive? Imagine that whole universe out there with all its beauty and complexity and nobody to see it. Does that matter? Well, there you are. That's a philosophical issue. And very lastly, and I'm conscious that I've overrun a bit, I just want to quote Haldane, Possible Worlds, back in 1927. I have no doubt that in reality the future will be vastly more surprising than anything I can imagine, meaning him, of course. Now his own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. And I think that is perhaps the thing, the arrogance of thinking we know it. We know enough to know everything. So I'm going to put the lights on now, and thank you very much for coming to listen to this. And I think we're allowed questions. Somebody else will tell me when we have to get out of here. Mehdi will. Yes?
Elon Musk recently suggested that we are a computer simulation.
Oh, yes.
You know, there's a 1 in 2 billion chance that we are not one. Do you have a comment on that?
Yes, the suggestion, if everybody didn't hear that, is that we could be a computer simulation. And this arose in the context of the multiverse, there being so many, and the suggestion was that many of the universes would be simulations. And the way to test a simulation would be to look very carefully back into the past of our universe and see if there's a point where there's a slight disconnect, where somebody might have changed a constant of nature very slightly to make it work better. I mean, it sounds a bit flippant, but it's not entirely flippant. And if you think the idea of a computer simulation for the universe is crazy, then just bear with me a moment. You will be aware how computer games have advanced, how you can now wear a headpiece and experience the virtual world, how people talk about wearing gloves, and you can experience through the sense of touch as well as the sense of sight and the sense of sound and perhaps the sense of smell. You can easily imagine a world with today's technology where, by dressing up in all this gear and putting on the stuff, we could have experiences and sensations that were far more exciting and more varied than anything we have in the real world. Now, I think that's quite frightening, and I think that should be perhaps one of the threats. I think it's quite easy to imagine that situation. So we're getting close to the point where you could imagine that we could be a simulation, because essentially the way we experience the world is a very narrow experience of the total reality through our senses. And so it's a possibility that we could be part of this virtual simulation, because you can begin to perceive yourself how an individual could experience a virtual world that might be more engrossing, more rewarding than their ability to experience the real world. And you already get a sense of that with people who who get involved in gaming and disconnect from everybody else. So I think it's a very clear possibility in cosmology, and when I suggested the test that we look carefully to see if there are any discrepancies anywhere, that's the best I can suggest for that. Yes?
Thank you very much. That was fantastic.
Oh.
Could it be a mode of an inability to communicate? There could be other civilizations that don't have the communicative features that we have.
Yes.
So
Oh yes, I think that you're raising the possibility that there might be other civilizations that are communicating in a way that we cannot either perceive or understand. And I think, of course, there are many issues like that. The only and certainly when I gave this talk and there were some linguists in the audience, I don't know if you're a linguist, they considered that our ability to communicate was essentially non-existent. And I think because they were thinking in terms of poetry and emotion and things like that. Now, I, as a physicist, the thing I like about the universe is the laws of physics are universal right through, so that whoever communicates with us will have a common experience of physics and possibly mathematics, and that we may be never able to exchange poetry, but we will perhaps be able certainly to share a common experience of, say, the uncertainty principle or the Planck function or something, and perhaps go further and perhaps even share technologies. And I suspect, you know, forming images, you think, would be pretty similar throughout the universe, and so we could exchange images. So I'm quite optimistic, unlike the linguists. Yes?
You mentioned a super theory, the 10 to 100 different universes.
Yes.
I don't know how you explore those other universes, and what's the likelihood of that anyway?
Well, I think, yes, I don't know. This is the question about, I mentioned the 10, it was actually the 600, but don't worry. Don't worry, because there are only 10 to the 80 or so protons in the entire observable universe. So 10 to the 600 or 10 to the 100 is an absolutely unimaginable number. It's something that string theorists who think that the true reality of the universe may be an 11-dimensional structure in which we are confined to just 3 dimensions of space and 1 of time. So we are like a surface within that high dimensional structure. And it comes out, string theory essentially seems to be a problem in geometry, to my mind, and it comes out of the number of possible combinations of something. Now, the problem with string theory is, although many consider it is the only hope we have to understand the center of black holes and the ultimate origin of the universe, it has not yet managed to make any testable predictions in our observable universe. It's entirely a mathematical construct. And you're quite right, there would be no way that we could experience any of the other universes. Although I have heard it by serious cosmologists said that the reason the force of gravity is so much weaker than the electromagnetic force is because the force of gravity works through the entire 11 dimensions, and the electromagnetic forces are confined to the 3 dimensions. So, in other words, if there was in an adjacent brane another universe, maybe a centimetre away, we may experience the gravity from that universe in some way, even if we can't experience anything else. But that's all. I like to stick to the observable universe. Yes?
You talked about life arising maybe out of other chemical elements, maybe based on ammonia as a solvent.
Yes.
Is the combination of chemical elements that life needs to work, is there a finite set based on our knowledge of chemistry?
Well, we have a very good idea of the chemistry required for our life to work. Carbon, hydrogen, oxygen, nitrogen, phosphorus. I think there are a few other key substances that work. So So talking about different solvents is a little bit of speculation that we could be looking at some carbon chemistry that perhaps operated with a different solvent, or we know that silica can also behave a little bit like carbon. It's less stable, so it can only operate at lower temperatures. It was said if we brought life, if say there was life on the moon of Titan and we brought it to Earth, it would just spontaneously combust. Now, I don't think anybody has done a detailed study of all the possibilities of the chemistries of life, but certainly carbon is the richest source because of its ability to form bonds with itself. Yeah. Yes.
Please, do you think human evolution is still in progress?
If so, yes.
What are we progressing towards?
Well, that's a very interesting question because, of course, evolution is driven by the process of survival. So, and what we see in our society is, because of the advance of medicine, that that all kinds of people who would not have survived can now survive. So you don't get the feeling that we are at present selecting any particular physical trait that enhances our survival. But, I mean, I just actually, you mentioned that, I just picked up, you pick up in things like New Scientist, these kind of almost throwaway lines, and it was looking at breeding success amongst a population of females somewhere, female humans, and it showed that that on average, short, thick-set women tended to have more children than tall, slender women. So you might say that over time we are going to select for shorter, more thick-set females. I think there are also, I don't know, there are people who talk, talk about possible changes in the jaw structure and things like that, less robust. But we would expect the evolutionary processes to be continuing, but of course we are now at the point where we're going to get to the point where we can interfere with the human genome, so things might move in very different directions.
The recent evolution has been in the human brain.
Oh yes, and we're still, I mean, human children have to be born before they're fully mature because of the size of the brain, so they need a lot of nurturing.
Other primates give birth more easily.
Give birth more easily, and if you look at some mammals, they give birth, and the animals, the calf is standing up and running around within hours. So, yeah, so we're probably still, but because of modern medicine, all kinds of potential problems are eliminated. Yeah.
Thank you so much. Just a very mundane question. The cave that you showed us, where the stalagmites were used, whereabouts?
Let me just see. Where is the cave in which the stalagmites, let me just show you that, are found? I don't want to guess. It's either France or Spain, but I expect everybody knew that. Now, where is it? I've got to find where it is in the sequence. It's back here, isn't it? It's there. Right, view, play slideshow. Right, it is 176,000-year-old evidence. Oh, I've only got the reference, I'm sorry. It's Joe Bear et al., 2nd of June, Nature, 2016. Does anybody else remember where the cave is? But otherwise, I'm afraid you'll have to, if you look on the web, Nature's a magazine, and go to the 2nd of June issue this month, you'll see a description of it. Yeah. Yeah. Any other questions? Yes.
What do you know about the experiment to send a probe to Alpha Centauri at high-speed probe, much faster than the escape velocity of rockets?
Yes, there is a proposal. Our nearest star is 4.4 light years away. So what would be, so I mean, if we could send something close to the speed of light, we could get something to go there and come back within, 8 years, 9, 10 years is actually less than the typical lifetime of a lot of space missions from proposal to launch. So, it would be a real experiment. Now, I haven't read much about this, but the ideas seem, in order to get those high speeds, the best way to do it would be to launch something up outside the Earth into the solar system and then fire a laser beam at it. And the thing is, light has momentum. So light can, if you reflect a beam, you'll get twice the momentum. So by shining a laser beam at this thing, we could accelerate it, and we could go on accelerating, because the beam is traveling at the speed of light. In principle, we could get the thing moving up to the speed of light, but that wouldn't, well, there are energetic problems. How would you stop it? Yes, that's a good point. Because I think the idea was that you would send a whole huge swarm of these things, and so that when some of them would then get into the gravitational potential well of Proxima, and then they might, and some of them would fall in, some of them would then whiz around and come back almost at the speed of light, so their trajectories would be changed. So, yeah, it's a good point. Switch off the light. Yeah, no, but you've got to decelerate them then. Now, there would be some interstellar gas that would slow them down, and you might say if you switched off the light at the right moment, the radiation pressure of Proxima would slow them down. Then how'd you get them back? Oh dear. Anyway, maybe you send a signal back. So there are lots of problems, and the major problems seem to be how do you deliver enough energy through the atmosphere to fire the laser? Maybe you build a laser on the moon, but so I don't know. Yeah. I mean, you say how do you get it back? We had that problem with going to Pluto. People said, why didn't the spacecraft go into orbit around Pluto instead of spending an hour shooting by? And it was going too fast. Now, if it had gone slowly enough to slow down, it would have taken too long to get there. So, it's a good question. Yes?
Is there a large queue of people wanting to think like you think, sort of backing up into the educational institutions?
I'm not quite sure I fully understand. Is there a large queue of people thinking the way I think, wanting to get into educational establishments? Do research. Well, there is the SETI Institute, which has 100 or so members. It's now being funded by a Russian oligarch, where there are people who, whose focus is on this. I think otherwise it is the sort of thing that people like myself do. I'm sure George Ellis here in Cape Town would have very different views from me, possibly, and people like Martin Rees. And they tend to think about these things and talk about them. So I suppose there is. I don't know. Yeah. Yes, it's a little bit the kind of airy-fairy thinking. So in educational institutions, they'd probably be doing hardcore electrodynamics or quantum chromodynamics, not speculating about life elsewhere in the universe. Any other? Yes.
There was a theory I heard the other day where people would travel long distance in space by bending space-time. So instead of traveling in one straight line, they bend space when you travel a small distance.
Yes.
If we advance technologically enough to do that, couldn't we just warp space-time and then send a signal to every existing star or planet and then... Okay.
The problem with bending, and you're quite right, matter bends space-time. But the problem is it's a very, very weak effect. So you need a huge amount of mass in order to do that. I mean, essentially, that's what a black hole is. It's a place where the space-time is isolated, is cut off from the universe. Now, in order to get the gravitational force to do that, you'd have to compress the whole Earth. Well, yeah, or a star, the Earth into about this size, or a star into about 20 kilometers or less. Now, it is possible if you find a very, very massive black hole, which there are in the universe, 3,000 million times the mass of the Sun. Now, as you approach the event horizon there, you could actually cross it in a rocket ship. If you went near the Sun that was a black hole, you'd be torn apart because the gravity on your feet would be so much stronger than on your head. But if you find don't worry, there are plenty of 3,000 million solar mass black holes around, then you could fly in and head towards the singularity. But sadly, you wouldn't be able to tell us what you discover. So it's a fun idea. Yeah. Well, could Mars be habitable for human beings? Mars, we think, in the past had an atmosphere and had water flowing and had seas. And so it could have been habitable then. We think it lost its atmosphere because its core is no longer convecting in iron, so there is no magnetic field, and so the atmosphere was stripped off. It's also less massive than the Earth, so gravity doesn't hold it. Now, people talk about going to Mars and what's called terraforming, so starting some chemical reactions or seeding it to create, it would have to be a temporary atmosphere. There are some tiny residual magnetic fields on Mars where we could build a kind of space station that would be protected from cosmic rays. So it's certainly plausible to go to Mars and develop, maybe build a greenhouse or something. But I think people talk about terraforming, but I suspect that would be a long way away to make Mars habitable. But you might say, yeah, we might need to do that as the Earth is too close to the Sun. Any other? Yes.
You mentioned the Great Quake, where they have, most of the variables now, but
yes.
The number of habitable planets, the lifetime of the civilization as well as the lifetime of the star.
Yes.
But what is the likelihood of, even if there is a civilization that is willing to communicate, the likelihood that their message will even receive us within the time frame that their civilization exists?
Yes, that's a good question. What's the likelihood of them being around when we receive their signal? Well, the answer is it's about 25,000 years to the center of the galaxy. So yes, it could be 10,000 years. And